Welcome, this is Professor Ridge, and today's lesson 1.6, Rational Expressions. And we'll start off with the first learning objective, simplifying rational expressions. Simplifying rational expressions. The quotient of two polynomial expressions is called a rational expression. Okay, so simply the root word here is ratio, right? So it's going to be a ratio of two polynomial expressions. So like in example 1 here, we have a polynomial for the numerator and a polynomial for the denominator. So this is what we call a rational expression. And a simple old fraction is also considered a rational expression. You can think of a whole number as a polynomial, a constant polynomial. Okay, so the process is, if you're given a rational expression, simplify it, factor the numerator and the denominator, and then you cancel any common factors, just like we would reduce a fraction. All right, so looking at example 1, we're going to factor the top. Hopefully you can recognize, oh, that's that difference of squares formula that we should really get to know like the back of our hand. So if you have a difference of squares, you're going to, it's going to square root each of the squares. So this will be A, this will be B, and then it'll be A plus B, A minus B. Okay, so the top will be x plus 3, x minus 3. And then on the bottom, we're going to, let's see, factors of 3 that add to 4. So we get x, factors of 3 that add to 4. Well, there's only one choice, 1 and 3. 1 plus 3 makes 4, so that works. The bigger sign gets this middle one, so this would be plus. And then to get a positive 3, they have to be the same sign, so be positive. All right, and you can see that now, once you've factored it out, the x plus 3, think of, anytime we have them in parentheses, think of this as one number. So no matter what x is, x plus 3 will be a number. So if, for instance, if x was 10, this would be 13. This number would also be 13. So these two numbers would cancel, and then we're left with these two numbers. Or I should say expressions, if we go back to thinking of it as polynomials. And then you just write down what's left over, and that's simplified. And there we go. The next learning objective, multiply rational expressions. Let's look at example 2. So to multiply these two rational expressions, I decided to switch it so I have more room here. We're going to first factor the numerator and the denominator. So again, this is a trinomial. So we need to, let's see, factors of 5 that subtract to 4. And so 5, their only choices again are 5 and 1. 5 minus 1 is 4, so that's going to work. The bigger one gets the middle sign. And to get a negative 5, when you multiply, these have to be opposite signs. And what I like to do is I go ahead and combine this as one big giant fraction, the times, because it's just like multiplying fractions. You're going to multiply the numerators, you're going to multiply the denominators. So I can just put it all as one big fraction. Okay, 2x minus 1 does not factor any further, so we'll leave it like that. 3x plus 18, well, we can divide a 3 out of both of these. And then the x plus 5. Oops, got to divide 3 out of that one. So we need to make that 18 divided by 3 would be 6. And then the x plus 5. And then let's see. So multiply the numerators, multiply the denominators, which is basically what I did. All right. And then I just combined those 3 steps. And then I am going to simplify, which is cancel any common factors. And again, when we're canceling, you can think of it as if I rearrange this and I do x divided by x plus 5 divided by x plus 5 is 1. So I can just cancel it, just like I would do with fractions. And then whatever's left over is your answer. And typically, even though technically this is not simplified, for rational expressions, we tend to break that rule for simplifying. We leave things factored out most of the time, just because if there's anything that we want to do with this, it's usually easier to work with it if it's factored already. So we just leave it that way. So that would be my answer there. Now let me see what the book says, if they actually go ahead and multiply it out. No, they leave it that way. So technically this isn't simplest form, but for rational expressions we tend to like to leave it factored. All right, on to dividing rational expressions. All right, let's look at example 3, dividing rational expressions. Divide the rational expression and express the quotient in simplest forms. So the process, you're going to rewrite the first rational expression multiplied by the reciprocal. So this basically just comes from, the dividing fractions rule. If I were to divide 2 fractions, you're going to multiply by the reciprocal. So that's our first step. So we're going to rewrite the top we're going to rewrite the example as we're going to take the first rational expression, leave it alone, and then multiply by the reciprocal of the second one. So flip it over, so it'll be x squared plus 2x plus 1 over x squared minus 4. Okay, now we're going to factor everything. And now it's basically a multiplication problem now. So again, I'm going to do all 3 of these steps together. So I will factor and put it as one big giant fraction bar. Let's see, factors of 12 that subtract to 1. So let's scratch work here. Factors 12 that subtract to 1, it's 3 and 4. So I have the 2x squared plus 3 and 4, so 4x minus 3x, that's the 1x, minus 6. I'm going to factor 2x out of the first one, so I get x plus 2. I'm going to factor a negative 3 out of the second one, so I get x plus 2. And then I have the common factor of the x plus 2, and then the 2x minus 3 left over for the other parenthesis. And if you multiply that out, you'll see that it equals 2x squared plus x minus 6. Okay, factors of 1 that add to 2. This is also, you can recognize it as a perfect square binomial, but I just like to think of it as 1 times 1. And then 1 plus 1 is 2, so x plus 1. And then this is a difference of squares. So that's the x plus 1 times the x minus 1. Difference of squares, x plus 2, x minus 2. So again, the different squares come up a lot. You want to be able to recognize the difference of squares. All right, now we're ready to cancel. So let's see, we got an x plus 2 cancels an x plus 2. And remember, this is basically, we're dividing and it's 1 and it basically goes away. Let's see what else. Looks like an x plus 1. X plus 1. And that's it. So now we just write down what's left over. We don't have to multiply it out. We can just leave it in the factored form, even though technically that's not simplified, but for most people, most algebra, people doing algebra would leave it factored. So we kind of consider this simple form for rational expressions. Okay, so we're basically seeing is it reduced when we say simplest form. Okay, on to the next learning objective, add and subtract rational expressions. Let's look at example 4, adding rational expressions, add the rational expression. So the guidelines here to do this is you're going to factor the numerator and denominator. Okay, there's nothing to factor in these. Then you're going to find the LCD of the expressions. Okay, so if you think of x and y as numbers, right, to find the LCD, you're going to take multiples of x and multiples of y and find a common denominator. Well, unfortunately, for this one, you're just going to multiply the x times y, and that will be the LCD. So let's see here. There's a whole lesson on how to do this, but you'll have to maybe search YouTube to find ways to find LCDs, or ask me in class sometime. Okay, so we're going to multiply the first one, multiply expression by a form 1 that changes the denominator to the LCD. This is what we want. So the first fraction, this is the way I think of it. I look at the factored form and I'm looking for x. I want xy. I already have the x, so I need to put in a y to get the common denominator. And you have to multiply by 1, so this is y divided by what? Y, which is 1. Don't cancel it because we're trying to build the common denominator. Now for 6 over y, y is the denominator, so you already got the y, so you need to put in the x. So we do x over x. And then we get 5 times y over xy, 6x over xy. Okay, now we're going to add the numerators and leave the denominator alone. So 5y plus 6x. And if you want, you can switch that order to put the x first and the y. It doesn't matter. Over xy. I would just leave it that way personally. And then you see if you can factor, reduce. In this case, you can't. So we're done. Now let's look at example 5, subtracting rational expressions. So subtract the rational expressions. And again, our first step is we're going to figure out what the LCD is. So we want to factor everything that we can. Typically, I don't factor the top. We're just going to look to see what the common denominator is. So if I have x squared plus 4x plus 4, and I factor that, that's x plus 2 times x plus 2. Or if you want to write it as powers, x plus 2 squared. And then for the x squared minus 4, that's going to factor to, that's the difference squares, x plus 2, x minus 2. And again, to find the LCD, here, let me tell you the process I use. So I'm going to look at the factored form. And for every factor, I need each factor the greatest number of times it happens in one of the factorizations. So do you see how I have 2 x plus 2's in this one and 1 x plus 2 in this factorization? So I need the greatest number of times a factor occurs in one of the factorization lists, if you want to think of it that way. So it happens, x plus 2 happens twice in the first one, once in the second one, so I need the greatest number of times it occurs. So I need 2 of them. Now if I want to do it with exponents, you can think of it the greatest exponent for that factor. So if you think of it as exponents, there's 1 here, 2 there, so I would need x plus 2 squared, right? Okay, so I like to look at it all factored out personally. That may be easier to understand for some of you though. Anyway, so now again I need every factor that occurs in any of the factorizations, but the greatest number of times that factor occurs in any one of the factorizations. Okay, so this one's done. I got everything here, and then x minus 2 happens once in this factorization and 0 times in that one. And so I need it the greatest number of times it happens. This looks like a 1 almost, huh? Okay, so I have x plus 2, x plus 2, x minus 2. So now, and again, the reason I like to do it all factored out, when I build my common denominator, I can look at the factors. So for the first one, I have the x plus 2 squared. I'm going to write it as x plus 2 twice. And now I got to build my common denominator. And here's a technique that I do too that I should show you. I don't like to think of minus. I like to think of it as add, the opposite. So I'm going to take this minus and I'm going to move it up. Now if this was like x plus 3, I would put parentheses x plus 3 and I've got to distribute the minus sign. Okay, so I'm going to change this minus to plus and move the minus up to the top. And then that way I don't mess up the sign. And then on the bottom here you got x plus 2, x minus 2. I hope I have enough room. Probably don't. Let's see here. So this is the LCD. Okay, I just moved it over so I can have some more room here. Okay, so now I'm going to look at the LCD. I got x plus 2 twice. So I'm going to do red for this one. So x plus 2 twice, and you see that I'm missing the x minus 2. So I need to put in the x minus 2 to build that LCD. Okay, and then I'll do blue. So do you see I have x plus 2, x minus 2. So I have the x plus 2, the x minus 2. So I'm missing the x plus 2. So I got to put in an x plus 2. So I just look at the factors. I don't have to do it like with numbers where you have to say, well, what this times what, right? You just look what's missing. Okay, and put it in. So now we have the LCD. We have the 3 factors that are going to be the same. Order doesn't matter. Okay, so then I'm going to multiply the numerators. So if you want, you can distribute the top, which I'm going to do. Plus, and then I'm going to distribute the top, so negative 2. I'm kind of combining 2 steps into one because I got common denominators. So negative 2 times x is negative 2x. Negative 2 times 2 is negative 4. And then since these are common denominators, I'm going to make one big fraction with the common denominator. If you want, you can do the square. I'm just going to go ahead and write it all out because I think it's easier when I get to the canceling stage just to leave it factored completely without using exponents. Unless it was like x plus 2 to the 7th, I'm going to write the 7th power. Alright, so I got combined like terms on the numerator, so 6x minus 2x is 4x. Negative 12 minus 4 is negative 16. And then the bottom is my LCD. So I got 2x plus 2's and an x minus 2. Alright, and then we're going to see if we can factor the numerator and if anything's going to cancel out. So let's see, we can divide a 4 out of the top and we get x minus 4. And then on the bottom, x plus 2, x plus 2, x minus 2. And as you can see, nothing will cancel, so we're done. That's simplified. And again, remember, technically it's when we're saying simplify for rational expressions, we're just seeing that it's reduced, right? Technically, that's not simplified form. We'd have to multiply it all out. But it's easier to do things with this fraction when it's all factored. You can see that it's reduced. If you had to add it with another fraction, you can build the common denominator easily. All right, so let's look at the next one. So moving on to the last learning objective, simplify complex rational expressions. Simplifying complex rational expressions. A complex rational expression is a rational expression that contains additional rational expressions in the numerator, the denominator, or both. Okay, so example would be if you had something, let's just do a fraction, right? If I had a fraction where you have a numerator, say 3/5, that's just a regular simple fraction. Okay, a complex fraction would have a fraction in the denominator and or in the that's the numerator, and or in the denominator, or both. So something like this would be a complex fraction, right? And then now take the fraction and put a rational expression there, basically polynomials. So if I had like x plus 5 over 2x plus 3 over x plus 1. This would be a complex rational expression. Okay, so you can have an additional rational expression either in the numerator, the denominator, or like at this fraction, I had it in both. So this one's a simple fraction, complex fraction, and then this is a complex rational expression. Okay, here's the technique to simplify it. You're going to combine the expressions in the numerator into a single rational expression. So you're going to make one fraction by adding or subtracting. Do the same thing to the denominator. So you want to end up with one fraction on top, one fraction on bottom. If the top's a whole number or just a single expression, you can put it over 1, basically. So then you're going to take the numerator and you're going to view this fraction bar as the divide sign. So it's going to be the numerator divided by the denominator. And then the way you divide two fractions is you're going to multiply by the reciprocal of the bottom. So you're going to rewrite the numerator divided by the denominator. You don't actually have to write it, just think of that. And then rewrite as multiplication, multiply, simplify. All right, let's look at an example. Example 6, simplify y plus 1 over x over y. So we got a rational expression in the numerator because of the 1 over x. We have a rational expression in the denominator. So our first step is we want to make this one fraction, one rational expression on the numerator. And do the same with the denominator for the second step. Well, that one's done. So on the top, you got to think of this as y over 1 plus 1 over x. So we want to get a common denominator for 1 and x would just be x. So we're going to multiply this one by x over x, which is going to get us xy over x plus 1 over x. We have common denominators. We'll leave it alone and then add the numerators. So xy plus 1. Okay, so the numerator becomes xy plus 1 over x. The denominator is already just a single fraction, so we can leave it alone. Then the next step was we're going to rewrite this as a multiplication division problem. So it's the top divided by the bottom. So the numerator. But again, I said you don't have to do that. You can just skip that. You're going to take the numerator, leave it alone, and you're going to rewrite this division problem. So we're going to think of that as division. So it's top divided by the bottom. So then we're going to leave the top alone, and then we're going to change divide to multiply. Right? The way you divide fractions is you multiply by the reciprocal. So that's the same rule for rational expressions. So now I'm going to multiply by y over x. Okay, and then I'm going to factor anything that I can factor. There's nothing to factor, so I multiply the numerators. I'm just going to put the y in front. X plus y, xy. Now when I say multiply, I don't really multiply. I'm just going to put it together as one fraction. Because the end result is I'm going to see if I can reduce. And basically there's nothing else I can factor. I mean, I can leave this as x times x, but there won't be any factors that are that can cancel. Okay, so then basically that's it. I'm done. Okay, that brings us to the end of the lesson. Make sure to practice in the exercise set, and I will see you next time.